Okay, so let us start. Today we continue our discussion about spin with a slightly new object. So until now, which is called spin orbit term. So until now, if I ask you what is the Hamiltonian of a nitrogen atom electron, you would write something like this. H equal to 1 over twice the mass, or the reduced mass, whatever. Let's call it M, just to P plus E over C, the vector potential describing the magnetic field. Then there is minus E squared over R, the standard Coulomb interaction. And then we discussed just yesterday, there is a new term where the field appears, and this new term is multiplying the spin, okay, the Zeeman term. So in absence of field, we get the usual thing. In the presence of field, we get a more complicated problem. In fact, this is in general a term that modifies the orbit. We explained a little bit what it gives origin to, essentially classically to the Lorentz force. We saw that for a uniform field, this was giving us, for instance, a term like this, where B dot L appears, angular momentum. Okay, so some term of potential energy, essentially of the type minus mu dot B, okay, where mu, you know, that is for electrons equal to minus mu B L, and therefore you get essentially from there a term mu B dot L, okay? Similar to this, except for this factor almost 2 that is there, okay? Now, well, at this stage, life is still pretty simple. I mean, the Hilbert space of the orbital part only really looks at this piece of the Hamiltonian, while the Hilbert space of the spin part only really looks at this part, okay? B is a field that is given, okay? So you don't need to worry about it, okay? So the spin lives by himself, and really the whole dynamics is governed by this piece of Hamiltonian in this space, and the orbit lives by itself, and the whole dynamics is governed by this piece of Hamiltonian in this space, okay? You can always really work with factorized state in some sense, okay? You can always work with state of this type, an orbital wave function times a spin wave function. There's no need to introduce any real mixing. We discussed that in general, given a basis of those states, phi n, and the basis of the spin state, for instance, the plus or minus 1/2 z states, we discussed that the most general state that you can form is not a factorized state, but rather a term of this type. Sum over n, some coefficient n plus phi n plus 1/2, plus another coefficient n minus times phi n times minus 1/2, okay? So this is the most general state. You see, it's a sum of products. This is an orbital times spin, orbital times spin. But in general, this is different from what you see here, okay? Unless these coefficients are very simple. For instance, if they are factorized as Cn alpha plus and the same Cn times an alpha minus, then you can obviously extract from here a coefficient Cn phi n, okay, out like this, and the alpha plus plus alpha minus minus reconstruct for you a most general spin state, okay? Is this clear? I want to make sure you clearly understand that the Hilbert space is made of product of things. However, that doesn't mean that all states you can form are just products. You can form sum of products, which is different, okay? So the most general state is this, and only for specific choices, which are factorized choices of the coefficients here, then you can really rewrite this as an orbital part times a spin part, like that. All right? Yeah.
Phi n is kept when to orbital in the space.
Mm-hmm.
Why we don't have L in this L?
Okay, he's asking why, if I have here states in the orbital Hilbert space, why I just indicate this with n. Sometimes I'm lazy and I really do not look again at the detail of the quantum numbers I am in front of. For an hydrogen atom, I should write here n, l, m. But more generally, even if this is not an hydrogen atom, it's some other Hamiltonian, I will have some quantum numbers, which I generically call n, okay? So sometimes, remember, I say, I have some Hamiltonian, let me consider the eigenstates of this Hamiltonian, let me call them phi n with eigenvalue En. Now, this n doesn't mean an integer, it means a label, okay? A label is much different than an integer, it's a label. The label can be very composite, it can be very complicated, it can be made of 3 integers, of an integer and a continuum label. It's just a way of distinguishing several objects, okay? So whenever I want to be just general, I use condensed notation where n now is a label. So you realize I'm writing sum over n, but this might be an integral, might be a sum and an integral, whatever, okay? Depending on what states your system, Hilbert space, is described with. I could choose a basis that is a basis of discrete states, a basis of continuous states, okay? For instance, in one dimension, I could expand anything in basis function of the harmonic oscillator. Even another Hamiltonian, even another problem. In principle, I could use that, okay, to describe any possible one-dimensional state, okay? So, except, for extended states that have to be, I could use plane waves on the contrary if I want to describe extended state. But never mind, okay, let me not enter into the details. What I really mean is that whenever I don't explicitly need to make reference to a certain specific problem where I should specify all labels, I often use this generic label n, which doesn't mean the principal quantum number of the hydrogen atom, okay? It means any label. This might be a very complicated Hamiltonian, okay? And the argument would be identical, okay? So once again, only for specific choices of the constants here, you do have a factorized states of this kind, okay? In general, you have a sum of product states, either this or that, summed, however, over all possibilities. Now, why I'm telling this? Because until really you have an Hamiltonian that is of this form, or more general, until the Hamiltonian is of this form. Oops. Is an orbital part times the identity in the spin sector plus identity in the orbital part times some Hamiltonian in the spin space, so some H spin, okay? Then, so if I have an Hamiltonian like this, I can always think of working with states that are of this type, okay? Essentially, this takes care of that. They look into each other only, and this takes care of that, and they look into each other, okay? I can always, I mean, unless I decide to start really from a combination of this type, I will always remain in the subspace, okay? Because if I start from a state like this, the evolution, okay, will be some unitary operator acting here, and due purely to this term, because the evolution operator, you see, these are two terms that really commute because they live in different spaces. So e to the minus I, this Hamiltonian T over h bar is nothing but e to the minus I, the orbital part times really an identity in the spin part, okay? So this acts in the orbital Hilbert space times e to the minus I, the spin Hamiltonian T over h bar, which lives in the spin Hilbert space. Okay? Is this clear? Okay? So if the Hamiltonian is of this type, you can always think of the two words being separate. Study the spin, study the orbit, and do two problems separately. However, there are cases where, and the lectures today is exactly devoted to this, you have new terms here that are not always of this type. Okay? So let us see the origin of this term. Obviously, this term must be of some relativistic origin, okay? Because if you think non-relativistically, that's all you have, for instance, for a hydrogen electron. Kinetic energy, possible terms due to the field, Coulomb term, and possibly, you see, this already has a relativistic aspects in it. You see, mu b is E h bar over 2mc. C is there, okay? This is also of relativistic origin in some sense, because the magnetic fields are, in some sense, strongly related to relativity. Okay. Yeah.
When you say relativistic effect, what do you mean? Because
I mean a very specific thing which will be clear in 5 minutes. So let's wait for a second. Yeah. Yeah.
The fact that the coefficients become equal to like the last term.
To this.
Yeah, is it due to a kind of symmetry?
No, this is a choice. If I choose the coefficients to be of this type, then I find a factorized state.
Is it just to choose?
Yes. I mean, the most general state is not factorizable, okay? But if I make some specific choice, I can obtain factorized states. Now, sometimes these are very useful because, in some sense, there are no terms that mix orbit and spin, and so you could think of working with states which are factorized. But there are cases, and we'll see spin orbit is one, where you must mix orbit and spin together. And in those cases, you don't write this thing in a factorized way. We will see in a second this, I mean, exactly this into play in a few minutes. Okay? So if this is clear, let me answer first to the question he was posing. If you have a relativistic particle, you know that the energy given a certain momentum, p, is not p squared over 2m. It's rather something like m squared c to the 4 plus p squared c squared. You remember this, right? This is a very famous Einstein relationship. Indeed, for momentum equal to 0, you get mc squared This is the famous formula, AE equal to mc squared. Okay? So, what happens? So this is a function like this. If you plot it, you see it starts from mc squared. And then if you expand, you get some term in p squared. We will see it's exactly the non-relativistic term. And then obviously if p becomes very large, this roughly goes linear in p sooner or later, right? So what I mean by relativistic correction, I mean that the formula is not exactly p squared over 2m. There are corrections to the kinetic energy which reduce the kinetic energy with respect to this, obviously. Okay, let's calculate them. Obviously, I want to expand in p, so let me put this outside, so mc squared, square root of 1 plus p squared c squared divided by m squared c to the fourth, okay? Or let me just, okay, like that. Now, you expand this as mc squared. The square root becomes 1 plus 1/2 this term. This is simple to remember, and less simple, but I think still right, is that there is a -1/8, the square of this term. So p squared, m squared, c squared, square, plus other terms. I think it's 1/8, but check, okay? Never mind. I'll see now after the calculation if this is correct. Okay, so let us now multiply by mc squared. I get mc squared, as promised, plus. You see here, mc squared cancels this c squared there, okay? And there is only one m remaining with a factor of 1/2, p squared over 2m. This is what we always use, okay? We never care about mc squared, not because it's 0. It's huge, in fact. The rest mass of the electron is huge compared to the Rydberg scale. It's of the order of mega electron volts, millions of electron volts, rather than 10 or 13. But in fact, it's so huge that you are not able to do anything with this mass. The mass always stays there. You don't take electrons and hit to each other at very large energies by breaking them and producing something else, as the particle physicists do, okay? You just look at them while they orbit at very low energies in an atom, or while they move in a solid, okay? So that's condensed matter physics. It's much low energies where the mass is there but never touched, okay? Therefore, you can just forget about it. That's why we never count it. You have to count, on the contrary, if you do high energy physics. So this is what all we keep. But you see that there is a correction to this, which is -1/8. Let's calculate. So the m and the c square really give me p square, and here I have m. So the c, there is a c squared term, because there is a c to the 4th times c squared, and there is an m cubed, right? M cubed. Okay, now you can rewrite this in the following way. I rewrite as p squared over 2m squared. You see, you recognize there is a 4 and an m squared. And then I have still to divide by mc squared. And still I need a factor 2. Okay? So I can rewrite this term like that. Now you see clearly why this term is small for all our purposes. If I ask you what is the average value of p squared over 2m of kinetic energy in a hydrogen atom, what would be your answer? I don't want a precise number, an order of magnitude. About 13, about a Rydberg, okay? I don't want to know if it is a Rydberg over 2 or a Rydberg, okay? It's about a Rydberg, okay? So the order of magnitude of this is a Rydberg, 13 electron volts squared, divided by the mass of the electron, mega electron volts, okay? So the ratio between this term and this term, you see there is a factor between these two, which is essentially p squared over 2m average divided by mc squared. I'm just taking this and divide by this to have the ratio. You see, this has this factor, 2 times this factor, okay? So 1 time I just disregard it. This is the ratio between this and this, which is obviously a pure number, okay? Energy divided by energy. So the Rydberg divided by the mass of the thing. Now, let me just write this, in fact, not as a Rydberg, but as, suppose that this is just a Hartree divided by mc squared, okay? Order of magnitude is the same. Now, a Hartree is equal to m e to the 4th divided by h bar squared. Then I have mc squared in the denominator. M goes. This ratio of two energies is therefore equal to E squared over h bar c squared. This is a very fundamental constant. E squared over h bar c, all very holy constants of nature, okay? The charge of the electron squared divided by h bar times c. This is called the fine structure constant. Fine structure constant. The reason for this name will be clear in a while when we will study in a better way the spectrum of hydrogen, accounting for these relativistic corrections, which we will do in perturbation theory later on. You will see that the degeneracy, for instance, between 2s and 2p will be split a little bit. So if you look carefully, you see a fine structure in those levels that were supposed to be totally degenerate, okay? And the amount of energy that the splitting has is exactly related to this quantity. Alpha, so this is called alpha, and you see that it appears squared. Now the value, the numerical value of this fine structure constant, notice it's a number, okay? We have a ratio of two energies, so this thing is a number. Now it's 1 over 137, roughly, okay? There is a lot of numerology, by the way, that goes around why exactly 1 over 137. So I receive mails from time to time by people saying, I have a theory of the world which explains everything because the sum of the squares of this thing, and if you invert it, I mean, it's obviously all, I mean, mental problems, but I mean, this number is small. This is not a mental problem. This is a small number, and therefore, and you have to square. And therefore, this gives you the gauge of the corrections that you get at the energies, at the energies that we work. So the non-relativistic part, the amount of corrections that you get from this term is very, very small. Nevertheless, can be quantified, okay? So I could keep this piece in my Hamiltonian here, okay? Obviously, I have to account for it in some approximate perturbative way. I cannot solve the problem exactly any longer, okay? We will keep this in perturbation theory later on, together with many other terms, with a couple of other terms, in fact. But the term so this answers your question, where these terms come from many places, for instance, from kinetic energy. And there is another term that I want to discuss today in more depth. So it's, yeah?
Why we call the defined structure constant?
Why we call the constant a constant, or the
Fine structure, what does it mean?
fine structure? This is what I was telling you exactly before. If you remember the spectrum of hydrogen, you have the 1s, and then you have the 2s, 2 spins, and the 2p, spin up, spin down, okay? And they are totally degenerate. Now, if you account for all terms that we are neglecting so far, so, for instance, that term, the spin orbit term, and another small term, which is still all of them of order alpha square, you will see that this becomes essentially the following structure. Four states remain there. Two states come down, and two other states are still degenerate with that. And this match, it's not in scale. I mean, this is of the order of really small numbers, while this is 10 electron volts. Okay, so this is really a fine structure. So that's the meaning. It's just small splittings. Okay, it's another way to say small splittings of the 2s2p and also 3s3p, whatever. In all places of the spectrum, this term gives you small splittings, okay, all proportional to alpha square. Okay. Now, let's eliminate this because this is not the center of our lecture today. It will come back later on as an exercise in perturbation theory. Let me leave this there. So let me discuss another physical term. Once again, all this would come from Dirac theory if we take the appropriate non-relativistic limit. So first start getting this, but you get other things. And let me discuss with you very, very heuristically. I don't pretend to give you a derivation of what I'm giving you. But you kind of understand the physics of it. I have this nucleus, okay, of some charge, for instance, plus 1. And this generates what? It generates an electric field, right? The electron is here. It feels an electric field. Okay, let me call E this electric field. How much will be? The electric field is obviously E over R square times the direction R, which I can also write as R divided by R. Okay? So this is the expression for this electric field, which the electron feels, and obviously this is the source of the attraction. Okay? Electrons are attracted to the nucleus. But now, the electron is moving with a certain velocity. Suppose that you sit on the electron. Imagine you sit on the electron and you watch the nucleus. Okay? In the reference frame of the electron, which is traveling with a certain velocity, what you see is a nucleus that is going with velocity minus v, right? So you, for looking from there, you see the nucleus really goes backward by minus v. But the nucleus is charged, okay? So this charge is moving with a certain velocity minus v, so what do you expect? A magnetic field. Well, yeah, in particular, a charge moving generates a magnetic field, like a wire of charges, okay? So you expect to see a magnetic field in your reference frame. I mean, if you look at this thing, there's really no magnetic field. There is an electric field from the nucleus point of view. But if you are an electron, you really feel an effective magnetic field of relativistic origin, obviously, due to the fact that the nucleus is really going back with velocity minus v. And the effective magnetic field that you feel is, well, essentially proportional to v over c dot E, the electric field that you have, okay? I'm not going to derive this, but I mean, from relativity, you can show that if you move with a certain velocity v in an electric field, you expect that there should be a magnetic field in that reference frame of this type.
Is this magnetic field real or just
Magnetic and electric fields depend on the reference frame, okay? So this answers your question. In the reference frame of the fixed nucleus, I mean, there is no magnetic field acting on the electron. In principle, you might say, well, but the electron moves, so it generates a magnetic field, but it's not a magnetic field that acts on the particle itself, okay? You want to know fields generated by other things, not self, okay? So you don't care about what magnetic field in the reference frame of the nucleus, the electron moving generates a magnetic field. which acts on the nucleus, on everything else. But I don't care of that, because that is not going to affect the motion of the electron in some sense, okay? It's a kind of self-interaction. You don't care. You want to know if something else is acting on you, okay? And if you sit on the electron and therefore you regard everything in that frame, you discover that there is this something else that is a magnetic field. In relativity, when you move, when you transform, you Lorentz transform from a system to another, the electric and magnetic field are transformed. And in this new system that moves with velocity v, you would see an effective magnetic field, which is a very reasonable thing, right? Because you see the nucleus moving. Reasonable, okay? I don't want to really do a rigorous proof. I mean, after all, this will be only an argument, not a proof. Okay. Now, you are the electron. You look and you see this magnetic field, and therefore this magnetic field acts on you now, okay? And it acts on you with what? With this term, okay? So you expect that there will be a new term in the Hamiltonian being mu b, the effective magnetic field, dot the spin. Notice I didn't put the factor 2. Yeah.
How is this magnetic field different from this one seen by the observer, which is on the nucleus? Is it different?
Repeat again.
How is this magnetic field different from this one, which an observer, which is in the nucleus,
Different from this? Okay, suppose that there is no magnetic field. So there is no term like this and no term like this. So the observer would see no magnetic field in the reference frame of the nucleus. Okay? The nucleus is there, standing still. It generates some electric field and no magnetic field. Okay? So there is no magnetic field in this frame. However, the electron in his frame feels not only the electric field, okay, due to the nucleus, which is there, but he feels also an effective magnetic field, okay? So these terms are not there, but he feels something like this. Okay? So how different is this from that? Well, this is 0. There's no magnetic field. This is a fictitious magnetic field seen by the electrons in his reference frame. Okay? So it's not a real magnetic field generated by the nucleus in the original reference frame. Is this clear? That's the reason why I put F. It's effective. Okay? It's not this. It should be confused with this. However, it originates a term that is very similar to this. Okay? I write it there. Is this clear? It's a heuristic derivation. So don't look at me as if I am. Is this reasonable? I want to know if it makes sense to your understanding. It makes sense. Okay? So even in absence of any real magnetic field, you expect that the electron will feel some form of magnetic field of this type, okay, which will generate and act on its spin in this way. Now, let us proceed a little bit with this calculation. So this is mu b, there's a minus, there is a v over c, and there is vector product with E. But E is, this is just minus. Let's exchange this two. So I get a minus sign. So this becomes a plus. Then I have the velocity over c. And here I have r over r cubed. Okay? And there is an extra E. Okay? Is this reasonable? Now let me add an extra mass in the numerator and denominator. So I have mu b, E, another mass, a mass in the denominator, a C, an R cube, and then I have M, well, R, MV, And that's it, right? I've accounted for everything. Just rewritten the same thing with an extra mass here and there. But you see that this is R vector P. So this is the angular momentum, okay? So the angular momentum appears here. So this is equal to mu B E over mc, 1 over r cubed, angular momentum, okay? This is only this term. I should here take a scalar product with S everywhere. So, okay? So you see that the spin and the angular momentum, indeed, they see each other in a scalar product type of way. The scalar product is reasonable. I mean, it's the only invariant under rotation object that you can imagine, okay? Is this clear? So in absence of magnetic field, there is some form of rotational invariance preserved, but only with L dot S. So you couple L and S. There is no magnetic field, but the two guys see each other. And now you could, so this object in front of here is often called lambda spin orbit. It's a function of R, I should warn you. So it's not just a constant, it's a function of R. Therefore, but you see, it depends only on the distance, not on the angles, okay? So in some sense, it takes care of modifying the radial function, okay? While these two pieces here, angular momentum and spin, operate on spin coordinates, so the spin state, and the angular parts of the function, the spherical harmonics, okay? They do not depend on R. Okay, so you understand that there is still some kind of separation of variables between radial and angular, but the angular and the spin are married now, okay? Let us see the order of magnitude of this. I mean, I promise that this should be small corrections. Let's see. Let us write the order of magnitude of this lambda spin orbit. And whenever I have an order of magnitude, I can substitute a reasonable scale for instance, the distance, which the most reasonable thing is the Bohr radius, right? So this would be mu b, the energy, the electron charge divided by mc, the Bohr radius cubed. Okay? Sorry. When I write L, really, I always assume, for instance, here, S is assumed to be without H bar, right? Because the H bar has gone into the Bohr magnitude. In the same spirit, let me write here an H bar and divide here L by H bar, okay? So from now on, I will write simply L instead of L of H bar, but all the H bar factors are really here, not neither in L nor in S, in a democratic way, okay? So with this new name, now L is this, okay? So L is really this divided by H bar. Okay, now if I have the H bar, now you see quite clearly that here I have, if I add the factor 2, what is this? E H bar over 2mc is the Bohr magneton. So this thing is just 2. The Bohr magneton square divided by the Bohr length cubed. Okay? Now, if I have two magnetic moments interacting at a distance a, b, they interact with a magnetic dipole interaction, which would have exactly this energy, order of magnitude, okay? So these are like two Bohr magnetons interacting at a distance AB. You might say, okay, so what? Well, no. it's important. These are small things. So magnetic couplings are pretty small, and the interaction of two small magnets is very small. Let us see. If you substitute now the expression for AB and T. So for instance, AB is equal to h bar square over m e square. And mu b, as we said, is equal to e h bar over 2 mc. So let's see. All in all, I have here 2. Then I have e square h bar square over 4m square c square, coming from here. The 4 is not important. Let me put it there. Divided by the cube of this. So h bar square over m e square cubed. Okay? Lots of constants, but all universal constants, you see? So let us see. This is 1/2. What about e square? Let's see. E square gets, so this is really e to the 6, e to the 8, right? Then I have h bar square from here, and I divided by h bar to the 6, so really h bar to the 4th in the denominator. And then let's see the masses, m square, m cubed, so I have an m. Is this right? It looks right. Okay? Is this right? Let's see. I must have m e square over, and oh yes, it is quite right. And the c is still missing. Oh, c square here. Okay? So let me rearrange the things, and I have now m e to the 4th over twice h bar square times e to the 4th divided by h bar square c square. Okay? Now, you recognize this is the fine structure constant square. And this is the Rydberg. Okay? So even this term is Rydberg times alpha square, as promised. Okay? So much smaller than the Rydberg by 1 over 137 squared. Okay? So this term is there with a prefactor, which is, however, pretty small. Now, you might say, well, I shouldn't care then. Indeed, these are fine modifications, fine structures, small splittings in the hydrogen, which, however, can be measured because people know how to measure very well frequencies. Okay? So they can measure these things. And in fact, they were measured, and they are there. Okay? So you can test calculations, perturbative calculation, for instance, about the splittings with real experiments. Second, if you go down in the periodic table, the deep levels, for instance, the deep S states, well, and in general, all levels tend to be concentrated more and more into the nucleus. Remember that instead of E, there is ZE in the potential. The effective Bohr radius, you know that decreases by a factor Z. Okay? If you go back to our lecture on the hydrogen atom, you remember that we did the calculation with a generic Z, and we discovered that the effective Bohr radius is really the standard Bohr radius divided by Z. So the more Z is high, the smaller is the length scale. So here I would have things that have, you see immediately, a Z cube up. Okay? But also, there is also some other Z's coming out because of the charge in the numerator. So all in all, the spin orbit coupling of an atom of charge Z has an extra factor Z to the 4th with respect to this estimate we have made. Okay? So you can expect that as Z increases in the periodic table, this becomes a reasonable energy, okay? So, although pretty small for hydrogen, it increases in magnitude as you go down in the periodic table because of a factor z to the fourth. And therefore, it is generally important for heavy atoms, okay? So if you do calculations, for instance, quantum chemistry calculation for heavy atom, you don't forget about those terms, okay? Because they give you sizable corrections to the energies. Okay, so end of this interlude. Just saying that in general you expect that there will be some spin orbit term of this form plus other relativistic corrections that you should account for in perturbation theory. Is this clear until now? Don't worry. I mean, most of the formulas are in the notes or in the books. So you just have to be, I mean, you prefer to copy. Which H bar do you want to copy? I mean, these are simple calculations that you should possibly do yourself again to really make sure that you understand that all the H bars and E's and C's are in place. So I might force you to do it by just doing this, okay? Okay, so let us see. Suppose that I have no magnetic field, so I simplify a little bit my Hamiltonian. This becomes just a p square. I have no magnetic field, I said, so this is not there. So the Hamiltonian is simple enough. It's our hydrogen atom beloved object plus this one, L dot S, plus other terms that for the time being I don't care about. Let's look just at this. Now you see, there is a problem now. Although there is no magnetic field, the spin appears explicitly, and worse than that, it appears multiplied by L, okay? So explicitly, a term like that means Lz times Sz plus Lx Sx plus Ly Sy, okay? Now, suppose I have a wave function of the hydrogen atom as I was working until now. How would they look like? They would look factorized. They would look things like some NLM wave function for the orbit times some spin part, okay? So plus or minus 1/2 z or a mixture, I don't care, but just a factor, okay? Now, if it was only for this, there would be no problem because these are eigenstates of Lz and Sz separately, and therefore this object really respects them. They remain like that. But now let's look at the effect of these two objects. I can rewrite them. You remember that I was defining S plus and S minus to be Sx plus or minus I Sy, and in the same spirit as L plus and L minus are Lx plus or minus I Ly. Okay? By inverting the two, you can easily convince yourself that, for instance, Sx is equal to, help me, S plus S minus over 2. Sy is equal to S plus minus S minus over 2i, and similar expressions for Lx and Ly. Okay? So let us write these objects. So Lx, Ly, Sx plus Ly Sy. This is equal to, so L plus L minus over 2 from here times S plus S minus over 2 from here. Then I have an extra term that is plus L plus minus L minus over 2I times S plus minus S minus over 2I. Are you following? Okay, let's see. There is a term like, first of all, I and I is really a minus 1. So let me put the minus 1 here. Now they look almost the same, except for appearance of minus signs here and there. For instance, let us look at this. L plus S plus. You see there is a companion here, but there is a minus, so it doesn't care. Similar thing happened for this other. L minus S minus also get cancelled by this S minus L minus. So the only surviving ones are L plus S minus, which appears there and there, but now with the same sign, and the other, which is L minus S plus, which appears there and there with the same sign. So all in all, you see I have a factor 1/4, but I have two terms appearing in the 2, so there is a factor 2 times 1/4, and the two terms are L plus S minus plus L minus S plus. Okay? So 1/2 of this. Is this clear? So this is another way of writing this piece, which now looks a little bit easier to the understanding, and it tells you that these terms disturb the states, okay? For instance, this term tends to increase M by 1, and this term tends to decrease S by 1, and this does the opposite, okay? So you see immediately that when this piece of Hamiltonian acts on the state, one term is innocent, really doesn't do much, but the other two are nasty guys. They change the state, okay? Is this clear? And they mix to other states, states with different M, different spin. Obviously, these are states that, in some sense, are still degenerate because you are not changing the principal quantum number. You are changing just the spherical harmonics M, which we said doesn't make any difference. They are all degenerate, okay? So you see immediately that you are mixing states that are totally degenerate, but in a particular way that is commanded by this term. So the best thing you can do is if you can, rather than working with this basis, work directly with a basis that is the right mixture in some sense, okay? So let's see if we can sort out what the right mixture should be, okay? So to repeat, states with these states will have some radial function, okay? Then we'll have some spherical harmonics, and then we'll have some spin, plus or minus 1/2. I'm writing now in wave function type. Now, this and these are mixed by the last term. So, but they are totally degenerate because changing M and changing the spin in the spectrum of hydrogen atom makes no difference at all. Remember? I have here the 1s. 1s has no problem, by the way. 1s says L equals 0. You realize immediately that if L is 0, both this term, well, this gives you 0 effect, and even L plus and L minus give you 0 effect. So there's nothing you can do to the 1s atom. This term will have no effect to lowest order and perturbation theory on the state, which will remain there. However, the 2p, not the 2s. The 2s, again, have L equals 0, and they don't care. But the 2p have L equal 1, and they have M equal to plus 1, 0, minus 1, and they can have spin up or spin down. So you see that this term make a mess inside this space. They just mix plus with minus, okay? So let's see if we can understand how to sort out this mess. And the solution is pretty simple. Observe that L dot S is like, well, I better write. Consider the following object, L plus S. Now you might say, how can you sum things that are in different space? I mean, it's like summing apple and potatoes. Well, you know how to sum them, right? This is L identity in spin space, and this is identity in orbital space times S, okay? So you can sum apple and potatoes with this technique of mathematicians of putting the unity, okay? That's what they mean, exactly. They are, however, a reasonable operator, which acts on the orbit and on the spin in a separate way, sum. Now, is this an angular momentum? First question. Looks like, but to verify this, you should go back and, for instance, calculate what is Jx, Jy, and if this comes equal to I, Jz, and all the others also come, then you say that, yes, this is an angular momentum, all right? Leaving, however, now in the product space, not in this or in that separately. He has two legs, one in the other, okay? And he lives in both. But let's see, is this satisfied according to you? Let's see, you have this is Lx. Should I write the times 1? No. No. Okay, I write it times 1 plus 1 times Sx, commutator with Ly times 1 plus 1 times Sy, okay? How do you do this commutator? You do the commutator of this times that, for sure. And how much it is? This is equal to I Lz times 1, because the 1 is untouched, okay? Then you can do the commutator of this with that. And this is equal to plus I 1 times Sz. But what about the commutator of Lx and Sy, for instance? Or, okay, I mean, this is something that lives in another space, okay? So obviously they totally commute. They don't care about each other, okay? So the cross terms are really missing, okay? And because of that, you can collect again the two things, and this is now what? I, Jz, as promised, okay? So indeed, the thing works. It's a sum of two objects working in different spaces, and obviously the sum respects the usual commutation rule. So this is an angular momentum. And therefore, according to our theory, all its eigenstates should be classified by some integer j, m, which could be integer, half integers. The usual thing should apply here as well. Now, consider j square. J square, so jx square plus jz square plus jy square. You can also write it as L plus S square, right? By the definition. So the square of this is simply L square. You don't care for the 1. The 1 squared is 1, okay? Okay. Then there is the S square coming from the square of this. And then there is a term that comes from the cross product. But remember that the two terms commute. So this is quite like when you do the square of a binomial. It's the same thing. There are ones, you multiply, they don't care. So the result is 2L dot S. So exactly our candidate nasty guy is nothing but j square minus L square minus S square divided by 2. Okay? So another way of writing this is j square minus L square minus S square divided by 2. Okay? What's the advantage of this way of writing? That you immediately understand that the best way of tackling beasts like this is not working with eigenstates of, until now, we have used what? We have used, for this, L square and LZ. And for this, I have used S square and SZ, okay? However, if I renounce to these two guys, obviously keeping L square and S square untouched, so I always combine the same M from the same L, and projections from the same spin. Here the spin is 1/2. I never changed that, obviously, okay? So if I keep the same states, which are all eigenstate of L square and S square, but I try to form now eigenstates of J square, okay, rather than LZ and SZ. After all, LZ and SZ were not appearing in the Hamiltonian. So why do I insist in having them well-defined? It's a waste of time. It's a waste of energy in some sense. It's the most natural thing, I mean, if they are separated, obviously. But if they are coupled together, then the best thing to do is to take care of J square. He must be happy, not LZ and SC. All right? And in fact, you realize that, for instance, a good way of constructing the eigenstate of J square will immediately tell you if this term will increase or decrease, because after all, this is a positive constant, okay? So depending on the value of J square, you immediately can tell me how much this term will shift the energy, essentially, okay? So let us see if we can construct those eigenstates of J square. Is this clear until now? Because now everything will become a mess in a second. So let me make sure that you understood until now the origin of this term and the fact that it must be somehow sorted out from constructing eigenstates of J square. Clear or not? Okay, so if it is clear, or reasonably clear, let me do the following. Let me concentrate on a simple example rather than doing it very, very general. So remember this scheme here. I do have this L equal 1 states, 3 of them, okay? So they are essentially classified by L equal to 1 and M being 1, 0, or -1, and by the spin that I will call essentially sigma, sigma being plus or minus a half, okay? How should I call it? I want some label. S, oh, very good, S. Okay, so S could be plus or minus 1/2. So this is the spin along Z, and this is the orbital part of the wave function. Okay, these are eigenstates of LZ and SZ separately. Let's see. Yeah.
S is equal 1/2, SC doesn't change. Spin 1/2. But it's MS,
You suggest this to be S equal to 1/2 MS.
No. S is always equal to 1/2.
Yes,
Spin.
I wrote it.
Yes.
Yeah.
But MS changes.
Right. That's what I want to do. Okay, so I write this as L equal to 1. ML could be 1, 0, or -1. And then S equal to 1/2. MS equal to plus or minus 1/2. Okay? This is a very nice, complete notation, and we all agree. Clear. Very good. Okay. Sometimes I will perhaps make this shorter or even eliminate, okay, because they are always there. They don't change. But you know what I mean. Very good. Okay. Let us start forming a few states. For instance, what about an object like L equal 1, ML equal to plus 1 times S equal to 1/2, MS equal to plus 1/2. Okay? The maximum LZ and the maximum SZ. Okay? Product. Okay? Remember our discussion about the product things. In general, I have sum of products, but let's consider it just a product. First question. Is this an eigenstate, for instance, of JZ? The answer is yes. Okay? Any product is always an eigenstate of JZ. It's a very trivial thing. And the eigenvalue is just the sum of the two eigenvalues, right? It takes 1 second and 1 line to verify this. So what is JZ here? It's 1 plus 1 plus 1/2 times the same state. Let me make it shorter. So here I have ML equal to plus 1 and MS equal to plus 1/2. Okay? Do we agree on this? This is simple. The 1 comes from LZ. This is just LZ times the identity in the other plus the identity in the first times the spin. Okay? So LZ reads this part only, doesn't care about this, and gives to me the plus 1. SZ doesn't care about this, acts on this, and gives me the plus 1/2. All right? Okay, so this is just plus 3/2. Very good. So you immediately realize that this new object J should have at least a J of 3/2, at least, right? Because otherwise, how can it have an eigenvalue of JZ equal to 3/2? So J here must be at least 3/2. It might be higher, okay? And have, obviously, a state with J 3/2. But do you think that it could be higher than 3/2? Can you imagine another eigenstate of JZ with higher value of JZ? Obviously, the answer is no, right? I mean, the topmost you can make is plus 1 plus 1/2. So this is right the maximum JZ, which means that this must be also the value of J. So what I want to prove to you now is that this is indeed not only an eigenstate of JZ, but is also an eigenstate of J square, which is never a trivial fact, okay? JZ is always simple. J square is complicated in general. Now, there are several arguments to say that this must be an eigenstate of J square. One of the arguments it goes as follows. You see that J square, if I take here factor 2, J square is equal to L square plus S square plus 2L dot S. I write it here again. And this 2L dot S is also equal to 2LZSZ plus, remember there was a 1/2 S plus S minus, I erased it. So L plus S minus plus S minus, L minus S plus. Okay, now let's see. If I apply L squared to this state, what I get? I get a number that is L plus 1. L is 1, by the way, so I get 2. I can apply S squared, still an eigenstate of S squared. This, nice, eigenstate, 2 times 1 times 1/2. What about this? This is the nasty guy. This gives me 0, because L plus acting on this, no effect. And S plus acting on this, no effect. Okay? So indeed, the nasty guy has no effect on this state. Okay? So all in all, J square acting on this state, okay, the m equal to +1 and the ms equal to +1/2 is fixed. Okay, let's calculate. It is equal to L plus 1, so 2 plus S squared, which is 1/2 times 1/2 plus 1, so 3/4, plus 2 times 1 times 1/2, which is 1, okay? So this is 2 plus 3/4 plus 1, 3 plus 3/4, so how much it is? 12 plus 3, 15/4. 15/4 is what? It's just 3/2 times 3/2 plus 1. Okay? So it matches. This is indeed a J equal to 3/2 states. Okay? Very good. So we got our first eigenstate, indeed rather trivial. Okay? So this is J equal to 3/2, Jz equal to, or should I call it Mj? Mj equal to 3/2. Obviously, L is still 1. Okay, let me write it better. I want to have more space here. So another way of labeling this state is J equal to 3/2, Mj equal to plus 3/2, and obviously L equal 1, spin equal to 1/2. Okay? Well, it's the first, but also rather disappointing. Is a product, is a simple object. So you might say, well, you have done all this big thing just to obtain the usual thing, relabel. That's only the beginning. Now, you look at the miracle. Suppose that I ask you to calculate the friend of these guys. Okay, so I want, for instance, J equal to 3/2, Mj equal to plus 1/2. L equal 1, spin 1/2. Okay? What do? There is a very definite procedure to follow here. Whenever I know the top state of a multiplet, the procedure to get to the down one, you used it already to construct the spherical harmonics, is applying J minus, okay? J minus. So to construct this, I should do what? I should do J minus of this, of J equal to 3/2, Mj equal to 3/2. Let me omit this part, okay? It is always there, fixed, let me omit it. As I will always also omit this part and this part. Otherwise, the notation becomes too bulky, okay? Now, this looks almost right. Remember that there is always a square root, okay? And the square root is j plus 1 minus m minus 1. And in this case, m was 3/2, okay? So if you calculate this thing, how much is it? I think you get square root of 3, okay? Verify that you get the square root of 3 factor here. Okay, so the procedure is simple. Let me write the state. Should I start writing the state in some better way? Yes. Otherwise, we keep messing things. So the first state I wrote was J equal to 3/2, Mj equal to plus 3/2, and this was just ML equal to plus 1 times MS equal to plus 1/2. Now I will construct J equal to 3/2, Mj equal to plus 1/2, and see what happens, okay? And then I will have to construct J equal to 3/2, Mj equal to minus 3/2, and then j equal to 3/2 mj equal to minus 3/2. Well, huh? Minus a half. Okay, so this is the 4 objects. After all, j equals 3/2 as 2j plus 1, 4 friends. Okay? Now, maybe the last one you imagine what will be just the opposite of this. So ml equal to minus 1, ms equal to minus 1/2. Indeed, this will come out. Huh? The 2 non-trivial things are these 2 guys. Okay? And the first one we are calculating here. So this m equal to 1/2 is just 1 over root 3 L minus. Sorry, J minus. Now, J minus is L minus times the identity plus identity times S minus. Okay? And now you see immediately that you get, when you act with L minus on this, remember this is nothing but this, L minus will decrease ML by 1. Okay, so we will give you ML equal to 0, while the spin is the same, plus 1/2. L minus will also give you a square root of 2, if you remember. Plus, S minus doesn't care about this first piece, which remains, therefore, plus 1, but cares about this, which becomes minus 1. And there is no square root of factor. I mean, it's 1. Okay? Now you see the bizarre thing. You started from a product state. Where was it? Here. This one. You applied L minus plus S minus, so a sum of 2 things living in the 2 subspace, and you got the sum of 2 product states. Not the product state. This is not the product. It's the sum of 2 elements. Each of them is a product. But you see, you cannot factorize anything here. You see, there's no common factor in it. You see that JZ is obvious. It's plus 1/2, 1 minus 1/2, plus 1/2 in both. Okay? So this is a very natural JZ equal to 1/2. All right? As we wanted to have. But the right mixture that you have to take of the 2 possible candidate states that are these 2 products requires a precise coefficient, square root of 2 over 3 and 1 over square root of 3. Is this clear? So let me write it like this. Okay? Only if you take this precise combination, out of these 2 eigenstates that are the product, you obtain the right eigenvector of J square with eigenvalue Jz. Okay? So in other words, here I should write root 2 over 3, ML equal to 0, MS equal to plus 1/2, plus 1 over 3, ML equal to plus 1, MS equal to minus 1/2. Is this clear? So we saw, for the first time, a state that is not a product. It's a sum of 2 products. And they naturally emerge when you study eigenstate of J square. Not of Jz, not of L and S separately. Okay? So these are the good combinations which make this term happy. Because these are eigenstate of J square, of L square and O square. And therefore, they are eigenstates of L dot S. You realize the little miracle that has happened. By combining things appropriately, all degenerate, so they don't care about each other, the energy would be the same, I make the right combination, which makes this guy happy. Because this is an eigenstate of J square. Okay? Now, I could proceed, obviously. And to get this, I should apply again J minus to that. And the result is very, very simple. J minus there is still a factor, a square root factor to take care of. Let me just write the results, okay? Otherwise, so you will find essentially square root of 2/3 ml equal to 0, ms equal to -1/2. And then I think I must erase the general states here, plus wait, what is it? Oh, just a second, huh? I get the right thing. 0 or -1, so it comes from there, plus 1/√3 ml equal to -1, ms equal to +1. Okay? Yes. Okay? And nothing, no mystery really. Don't try to calculate by heart. There are a few square roots to take care of. The square root of the L minus, and also the square root coming from the J minus, which is, however, this time different because M has changed. Okay? If you do it properly, you will understand that this is the correct result. Now, and if you keep applying J minus, you get this simple object here. Now you see what you got. Out of the 6 original states, remember I have 3 and 3. M equal to +1, 0, -1, ml, and ms equal to +1/2, -1/2. Okay? So total 6 states. 4 have been reshuffled in constructing these 4 states. But there are 2 missing things. Okay? After all, out of the 2, for instance, JZ state that you can think of, JZ with, for instance, JZ equal to +1/2, okay? I have formed only a precise combination here, but there is one that is missing. And the same happens for JZ equal to -1/2. This is not the only state you can form. You realize that you can make combination with some minus signs also, which have not been accounted. All these have plus signs. Okay? So the question is, what is missing? And this is a chapter of this theory, which is addition of angular momentum. The theory tells you that if you sum an angular momentum, in this case L equal 1, plus a spin, in this case, for instance, 1/2, then what you get out of that is a total J, which can go from the maximum that you can get, so L plus S, which is in this case 3/2, down to L minus S, which in this case is 1/2. Now, this might seem like a trivial case, but I mean, in general, you could have higher L and even higher spin, and these 2 things might be several half integer or integers distant by 1, okay? The J that you construct are all with the same, for instance, in this case, all half integers. Now, rather than doing the general theory, I'm just giving you an example. But the general theory would be quite mimicking what we are doing. It's just more, I mean, a little bit more abstract, but it does exactly what we do. Now, you might ask, why do I want to construct a general sum of 2 angular momenta? Well, because in other problems, you might have to do things with higher values of. First of all, if you want to study this fine structure constant of these states, for instance, there will be obviously, corrections to the D state. The D states have L equal 2. And therefore, you have to do the same procedure now with L equal 2 and spin 1/2. All right? But there is even more than that. When you do several electrons, you start combining the spin of the electrons together, the angular momenta of the various electrons together, and then you have to do sum of several things, and you can get easily to higher number, okay? So there is a need for, knowing how to do this thing more in general, okay? But I better prefer that you have clear in mind what is the procedure. If you really have to do this then in a definite problem, then chances are that you might look in the book what is the coefficients that you need to put in these combinations, because they are absolutely tabulated. These coefficients are called Clebsch-Gordon coefficients. So whenever needed for a very large J case, for instance, you can look in the book. But it is important that you know how to construct them yourself. Given some patience and some square roots, you can do it. There is no mystery, okay? So this first I showed to you. It's just application of J minus. Now there is a slightly more complicated aspect of the thing. How do I construct the missing guys? There must be 2, right? Because these are 4, there must be 2 other states missing. And now let me explain to you how you do it. You can do it in a couple of possible ways. Okay. One possible way is the following. I do have these 2 objects here, which I combined in this state with these 2 coefficients. Okay? So it's ML equal to 0 and MS equal to plus 1/2, and the other is ML equal to plus 1, MS equal to minus 1/2. They both have JZ, as we said, equal to plus 1/2. However, I can, in general, make a combination with 2 arbitrary constants, alpha and beta. And I want to construct out of this an object that is not only with JZ equal to 1/2, but with a definite J. Okay? Now, obviously, J cannot be 3/2. J obviously cannot be also smaller than 1/2. Okay? Why? Because otherwise I shouldn't have JZ equal to 1/2. So J must be 1/2. Now, the goal is this. How do I form a state with J equal to 1/2 out of these 2 guys? 2 possible strategies. The first is, okay, if this must be the top state now of a J equal to 1/2, it means that if I apply J plus to this guy, I should obtain 0. Okay? Is this clear? This is the first strategy. The second strategy is, if this is this state, then it should be orthogonal to this. Okay? In both ways, you get exactly the same prescription. I mean, look, if I want something that is orthogonal to that, there is a very simple procedure. Is, for instance, let's put 1 over root 3 there and minus 2 over root 3 on the other. Now, you see immediately that this times that minus that times that is just 0. Okay? So this is the obvious choice. So you can either put alpha and beta and just calculate the scalar product and determine that the alpha and the beta must be that, or use this strategy. Okay? So let us use this. So this was, again, alpha, and this was beta. So if I apply J plus to here, what I get? I get square root of 2, the state ML equal to plus 1, MS equal to plus 1/2, okay, from the L plus times alpha, obviously. Plus, so I'm trying to determine alpha and beta, okay? Suppose that I don't know them. I apply L plus, and this gives me this, plus, well, L plus acting on this gives me 0. Okay, good. Plus S plus. S plus on this gives me 0, but on this gives me just beta, ML equal to plus 1, MS equal to plus 1/2. Okay, you see, you have the same state. Okay, so you can collect the things, and you have square root of 2 alpha plus beta in front of this state. But in order for this to be 0, the only possibility is that square root of 2 alpha plus beta is just 0. Okay? And you see that one solution, an obvious solution of this, I mean, you can find several solutions, but then you have to normalize. And you immediately see that if you take alpha equal to 1 over root 3 and this equal to minus 2 over root 3, you get 0. Okay? So this is the solution. So to summarize, the other guys have 1 over root 3 and now a minus 2 over root 3. Okay? And obviously, if I calculate the J minus of this, I get two other states that are made of the same ingredients of this with two new coefficients and a minus sign between them. Should I write? Why not? It would be minus root 1 over third 1, 0 plus 1 half, sorry, 0, and plus root 2 over 3 ml equal to minus 1 minus plus 1 half. No, I have it wrong here. I'm sorry, I have this thing wrong. There is a misprint in the notes, I think. In any case, I think that this is the solution. Yes, you see that this times that plus this times that is 0. Mm-hmm. Okay, so this is a state with j equal to 1/2 and jz equal to minus 1/2. Okay, so summary. The right combinations that make L dot S happy are the same ones that make J square happy. So you have to take the product state of ML and MS and construct appropriate combination through these Clebsch-Gordon coefficients that are obtained by square root of L plus, L minus, S plus, and minus things, okay? And get eigenstate of J square. This is the example we did. You can repeat the same exercise, for instance, for L equal 2, just to get some hand in the procedure, and you should be able to construct states of 5/2 and states of 3/2. Okay, these are 6 states, and these are 4 states, and these are 5, and these are 2, so total 10. All right. So try to do this, and this is more than enough, I think, to grasp addition of angular momentum. Okay? So I'll see you tomorrow.